In this section, we're only going to look a little bit at polar graphs. There's a lot of polar graphs out there, very cool looking graphs, beautiful in fact sometimes. I just kind of want to focus on just some fundamentals of what a graph of a polar equation would look like and how to do basic graphs. So most of what you're going to do in this section is be able to graph circles. So circles are the graphs that are in the red box here. There's either a circle centered at 0, or there's a circle that's centered just where it's sort of adjacent to 0. And so that means when we have cosine, it could be over here. You see where that left side touches 0? Or if the radius is negative, that would put a circle on the left side. And for sine, we'd have a circle above the origin, and if the radius was negative, that would create a circle below. And I'll talk more about that when we actually do the examples. Here's some more examples of polar graphs. Like I said, we're going to focus on circles. There are a couple questions on the homework that just ask you to, given the equation, identify the type of graph. And so for those, you know, you don't have to memorize anything from this table. This table is actually also in the textbook, but just know that you can, for those homework questions, go back and look at this table just to see, you know, it might be like, oh, okay, I can see that it's of this form of, like, for example, if I put numbers in here, a rose graph like this would be something like r is equal to 5 sine of 2 theta. That would indicate that it's a rose graph. And one thing you can see here, just to kind of talk a little bit about the roses, because they are common polar graphs, is that when you have an even angle, the number of petals is going to be doubled. So 2 theta would give 4 petals. And you see how here this is a 4 theta. If you count them, you have 8 petals. 1, 2, 3, 4, 5, 6, 7, 8. As opposed to if you're dealing with an odd one, like 3 theta, that actually indicates the number of petals. So 3 theta means 3 petals, where 5 theta means 5 petals. Okay, but again, not anything for you to try and memorize. Okay, let's look at this first one. Here's probably the most basic type of polar graph that you might see, which is if we have the graph of r is equal to 6. So this means the radius, this means the radius is equal to 6, but that the theta could be anything. So if we think about some points where that might happen is, let's say if we go out 1, 2, 3, 4, 5, 6 here, this would be 6 with a 0 angle. This would be 6 with a pi over 6 angle. This here would be 6 with a pi over 2 angle. So you might be getting the idea now, but if we just plotted all of those points, we would end up with a circle, this circle, with the center at the pole, and the radius is equal to 6. So that's the graph of r is equal to 6. So this is similar, but a little different. This is similar in that we're only given theta. So here it's saying the angle is pi over 4, but when you don't see the r value, that means that r could be anything. Kind of as a side note too, if you think about that, similar to when we have horizontal and vertical equations in the regular xy coordinate system, which is that y is equal to 5 means that y is always equal to 5 and x is anything because it's not there, and that creates this horizontal line where y is equal to 5. Okay, so if we just know the angle, though, and the radius could be anything, if we think about that same idea of like, okay, let's just find some point where the angle is pi over 4. So I find pi over 4 here. Let's say right down here would be 1 and pi over 4. This point would be 2, comma, pi over 4. This would be 3 pi over 4, so you might be seeing the pattern here, is that it doesn't matter what the r is, but this is going to be where the angle is. And we could go in the other direction as well. So if we went here, this point, that would be -1 comma pi over 4, -2 pi over 4, and so on. So if we connect these dots together, what we have is a line that goes through the pole. So if we're just given an angle value and not a radius, it's going to be a line that goes through the pole at that specific angle. Okay, let's look at another example of a polar graph. Okay, so here's the type of circles that we're going to have to do a little bit more work with. So you could look back at the table. So you see how if we think about what to expect with a graph like this, so r is equal to 4 sine of theta. Let's go back to our table. That is actually going to be something like this. So you may be able to go here and actually just start graphing it. I kind of want to show where that graph comes from though. And to do that, what I want us to think first of is how we were graphing trig functions before, which is that instead of calling that r, we would say something like y is equal to 4 sine of theta, where here's our y-axis, here's our x-axis. We would look at it, we would say the amplitude is 4, so that means it goes up 1, 2, 3, 4, and then down 1, 2, 3, 4. So our graph is going to be in between 4 and -4. I'm going to just plot some points and then kind of show how this relates. So if we just think about this table that I have, what I'm doing is just trying to plug in values. So this first one is if I'm plugging in the angle measurement of 0, and I realize just to keep things consistent here, this graph that I have here, I'm trying to show how we would graph it if it were in y and x. Okay, so back to our polar graph though. 4 sine of theta, this means 4 sine of 0. And sine of 0 is 0, so this answer is 0. And then what about if we plug in pi over 4? So I won't do this for all of them, but if I do a quick sketch here, if I have a pi over 4 reference angle, that would be the 1, 1, square root of 2 special triangle. So sine is going to be 1 over square root of 2. And I realize I'm already kind of running out of space here, so let me write that. 4 sine pi over 4 is equal to 4 sine of 1 over square root of 2, or you might write that as square root of 2 over 2. So if you simplify that, that's 2 square root of 2. And what I want to do is I want to plug in the approximation so that I can actually try and plot it somewhere on the graph. So if I plug it in, we get that that's about 2.8. So I'm going to put 2.8. So pi over 2, and I haven't drawn any sketches like this yet, but just to show you that I don't usually do the triangles for the quadrantal angles. Instead, I think about it from the perspective of the unit circle, and I write these ordered pairs down. And then from there, I go the fact that sine would be the y value if it's the unit circle, and cosine would be the x value. So if it's pi over 2, that tells me that their sine is 1. So the answer here would be 4, because it's 4 times sine of pi over 2. 3 pi over 4, well, we've already kind of done the pi over 4, but if we move over to quadrant 2, really nothing changes for sine because it's still positive there. So this is going to be 2.8 again. If we plug in pi, sine is 0 there. So I'm going to put a 0, and then you start to notice it repeating. So now if we do 5 pi over 4, for a sine of 5 pi over 4, and I realize that I am going over this a little fast, so I'm just going to remind you that this is actually really like a review of the graphing that was done in section 4.6, if you wanted to look back at that. that section. Oh, not 4.6, I'm sorry. 4.5. Okay, so if I go and figure out 4 sine of 5 pi over 4, 4 times, if I draw the triangle down here, the same one with the reference angle of pi over 4, now the y value becomes negative because the y value is negative in quadrant 3. So I'm going to write that as negative square root of 2 over 2. So the answer is negative 2 square root of 2, which means it's about negative 2.8. And if we keep going, just kind of, if you notice, we're going all the way to 2 pi, so kind of one time around here. Sine is negative 1, so that would make it negative 4. 7 pi over 4 is going to be another negative 2.8. And if we plug back in 2 pi, it's the same as when we plugged in 0. So the answer is 0. So what I want you to think about for this table, where we just plugged in different values for the angle, so that we came up with different polar coordinates here that we can try to plug or plot on our graph. So let's try that. So the first point is 0, 0. So that's this point right here. Then we have that when we're dealing with pi over 4, the radius is about 2.8. So I'm going to go on that line, and I'm going to go up 1, 2, almost to 3, but not quite. Then we've got pi over 2. So that would go up to 4. So I'm going to go out to the radius of 4. 1, 2, 3, 4. Gets right here. Then we went to 3 pi over 4, and it's 2.8 again. So out 1, 2, close to 3, but not quite. And then when we go to pi, it goes back to 0 again. So this is kind of the shape we ended up with. I mean, if you just tried to connect them, you might be like, oh, okay, the graph looks like this. But it definitely has more of a smooth transition here. And to kind of show that, let me actually go back now to how we would graph this, like from section 4.5, if we were to graph y is equal to 4 sine of x. So the 5 key values, so I'm going to draw the 5 lines here. So 1, 2, 3, 4, 5. That really represents one full rotation before it starts repeating again. And so in this case, that would be 0, pi over 2, pi, 3 pi over 2, and 2 pi. So it's all the quadrantal angles, which are the 90-degree angles. And because this is just an x and not 2x or 5x or anything affecting the period, then I just leave them as those 5 key values. Then if we try to graph sine, so what helps me remember with sine is I always start at 0 and I end at 0, and then you go up and in the middle and then down. So that's the basic shape of the sine graph. So it looks like this. And so the table we have highlighted in green is like really kind of saying the same stuff as that blue graph is saying. And so how does that translate to our polar graph? Is let's think about it. So we start off at 0, 0, but then what happens is as we rotate around, as our angle gets bigger, the radius gets bigger up to 4. So that creates kind of like this shape where the angles are getting bigger and the radius is getting a little bit bigger and bigger. And then, right now we're at here, pi over 2. Now what happens between 0 and pi over 2 is that it's going to start getting smaller. So what happens is as we rotate around, our radius gets smaller and smaller and smaller and smaller until we get back to 0. So what's happening after that? This part is in the negative, so we're dealing with negative r values, and this is where we have to sort of go backwards on our polar graph. So I'm going to switch colors here to try and show that. So at pi we have 0, but now as you go from pi to 3 pi over 2, so that would be, rotating from here to there on our polar graph, our R values become negative, and they start smaller negative, and then they go up to -4. So if we think about that reversing, instead of, let's see, instead of pi over 4, we did 5 pi over 4 right here. If I plot that point, maybe I'll go back to my graph here, this table anyways. 5.4 and -2.8. 5.4, that means I go back I go back 2.8, so that would be 1, 2.8. And you see how it ends up in the exact same spot? And that's because for polar graphs, these two polar coordinates represent the same spot on the polar graph. And so then if we do 3 pi over 2, which is down here, it's not +4, it's -4. So that means we would go backwards 4, and that gets you to that same spot. So same thing for this pi over 2 and 3 pi over 2. So this second half of our graph, really, it's just going around the circle again. So what technically happens with the graph, if I plot from 0 to 2 pi, is it actually just goes around the same circle 2 times. So let me look at 7 pi over 4. That's another -2.8. So if I go backwards, 1, 2.8, that gives me right to that same spot here. And then it starts repeating. So the graph of 4 sine of theta is the circle where it goes around once, and then it went to pi, and then it goes around again as it goes to 2 pi. But the circle follows from what that original table was. So if it's 4 sine of theta, it's going to be a circle above the 0, where not the radius is 4, but the diameter. The diameter here is 4. So let's try another example. Now let's graph the equation r is equal to negative sine theta. So if we go back up to that table, remember if it was sine, it's either going to be a circle above or below. And the above is for the positive, and the below is for when it's negative. But I kind of want to just show how to graph it by thinking about plotting points as well. So to plot points, what I have here, I'm going to try to draw it as though it were a rectangular graph. So y is equal to negative sine of x. And so this is going to go between 7 and -7. Five key values. The x is not changed, so the period is going to be 2 pi. So I'm going to write those key values in. What does the graph of sine look like? So it starts, graph this in green, so it starts at 0, it ends at 0. That's always going to be the case for the sine graph, unless for some reason it gets shifted up or down. And it's also going to be 0 in the middle. And the -7, though, means that we start down instead of up. So it's going to go down here, and then it's going to go up there to 7. So this is the graph of negative sine of x. So from what we talked about before, this is going to be a circle graph that basically goes around the circle twice. The first set is going to be negative values. Those are a little bit harder to graph because you have to think about going backwards. So I think the best way to graph it is to just look at the positive part here, and I can try and graph those points. And so what this is saying is at pi, I have 0. So I'm just going to start here at 0. And then as I go to 3 pi over 2, the radius is going to be increasing until it gets to 7. So that creates kind of a shape that, oh, I guess I should have counted 7 first. Let me do that. 1, 2, 3, 4, 5, 6, 7. Right, I know my point has to go all the way down to here. So our graph is going to look something like this. It's getting bigger and bigger, and then the radius is going to keep getting smaller until it gets to 0. And so that's what our graph is going to look like. To get a better idea of what the graph looks like, you could always plot some extra points. Like maybe I'm like, I want to plot, 5 pi over 4. I might try to think about angles where I don't even get the square root too. So like if I think about the sine value, so if we're dealing with a 30-degree reference angle, sine would be 1/2. So maybe let's try, if we just wanted to put some extra points in here, we could try this one and this one. So if we wanted to figure out what's -7 sine of 7 pi over 6, so if I do 7 pi over 6, that's in quadrant 3 with a reference angle of pi over 6. So opposite of the 30 degrees is the 1, hypotenuse is 2, and then square root of 3, and then I check the positives and negatives. So this is a negative, square root of 3, -1. So this is going to be -7, and then sine is going to be -1/2. So that tells me it's a +7 over 2, which is 3.5. So I could get a better idea of my graph by plotting that point. So we found that the R value is 3.5 when the angle is 7 pi over 6. So let's see. That would be this point right here. So let me erase my graph right now, and then I'm just going to get these extra points. We could do the same thing for a reference angle over here. So if the pi over 6 is over here, it's going to be -1, positive square root of 3, and 2. So -7 sine, the actual angle that we're dealing with here is 11 pi over 6. That's equal to -7 times -1/2 again, so same thing. 7 over +7 over 2, just positive 3.5. So that point, 3.5 here. Now it can make it a little bit easier to try and graph the circle. I think I just didn't have it quite wide enough before. And so we get a circle that's below the x-axis, where the diameter, in this case, is 7.